Hello everyone. As Ingrid mentioned, I am doing PhD at University of Bergen in mathematics, and I am working on machine learning applications on acoustic data. My supervisors are Anne Olejnik from University of Bergen and Nils Olav Handegard from Institute of Marine Research. And my PhD project is also subject to the machine learning work package of the ClearMac project. If you would like to have more details, you can go through with this QR code. And today I'm going to present our very recent research work, Annotation-Free feature learning for improved acoustic target classification. And today I will first show you the structure of the acoustic data, also the collection and the classification. I will also show you a typical supervised learning framework applied on the acoustic data. Then I will discuss our motivation behind our research work and our proposed self-supervised learning framework. I will also discuss the sampling methodologies to train our self-supervised model and data selection and the procedures for the evaluation part. Finally, I will present our results and the future plans. So the acoustic data. So it is important to note that we use acoustics for underwater imaging instead of images, because water absorbs and scatters light much more than sound signals, sound waves, and electromagnetic waves propagate very poorly in the seawater, while acoustics are more effective for long range and high resolution sensing in the underwater environments. So the data collection part is done by the acoustic cruise surveys operated by the Institute of Marine Research, and we are using the underwater sound propagation systems such as the hull-mounted echo sounders. And the main overall objective here for this data collection is the estimation of fish abundance. This is the overall goal after collecting the data. And during those cruise surveys, we have a research vessel like this typically, and we have hull-mounted echo sounders here. Those devices are simply sending sound signals into the water, and those signals are reflected back from the objects in the water column. And those reflections, so-called backscatters, are read by those echo sounders again, and we have the resulting ping for each signal. And during the survey, those research vessels are also moving along the ocean, and eventually we cover some regions, and we have a two-dimensional array for each echo sounder operating with different frequencies. And for each echo sounder operating with different frequencies, we have a separate channel for our acoustic data. And eventually we have the data in this format, which has, we visualize them as echograms. We have three dimensions here: ping time, range, and frequency. So for the ping time represents the distance, and since the ship is moving along, the distance also depends on the vessel speed and the ping rate. And range stands for the depth here, which is dependent on the pulse duration. And we have the frequency. It is for, as I mentioned earlier, it is for each echo sounder. And this data is very extensive in size for each survey, because it can take just weeks to collect this data. This is just a representation of the data. It looks like a 4-channel image, but they are not images. We see some objects, and as you can see, we have the color bar here representing the energy level of the backscatter. So we still have some pixels, and each pixel is representing the energy level of the corresponding object on this location. And when we have our data, our experts in marine biology and physics, they are annotating the data, considering the target species, because each cruise survey is targeting one specific fish species. In our case, it is sandeel. So we are more interested in sandeel for this annotation process. So our experts are looking at, for example, this fish, and they check if it is sandeel, they annotate it as a sandeel. If it is a fish, but another type of fish, it could be anything else. It could be salmon, mackerel, or any other kind of fish. They annotate it as a separate class, other class. It means that other class can contain any kind of fish species apart from the target species. And all other objects are annotated as background. So we have three distinct classes here: other, background, and sandeel class. And when we have the annotated version of, we have the annotations, we use this mask to integrate the corresponding sandeel energies and then reach the estimation of fish abundance. This is the overall goal. And afterwards, I would like to present you a typical structure of a supervised learning framework applied on the acoustic data. This is a little different than the images, the procedure, because as I mentioned earlier, our data is very extensive in size, so data selection is needed here. What we have to do here is to extract patches by using some sort of predefined sampling criteria, and we have to feed them into our supervised learning framework. It could be anything, like, for example, unit architecture, patch classification, segmentation, anything else. We have to train our model. Of course, we also need annotations. We need to train, and our expected output is to use the data and then produce the same inputs for the test data set. So this is a typical structure of the supervised learning framework. But there are some challenges here. First one is that annotations are targeted. It means that we only have the fish species annotation. So if we want to examine, for example, let's say other structures, like, for example, zooplankton layers or some kind of other structures, we need to have them annotated, but they are not annotated at all in our data structures. Also, another thing is that annotations are not precise in our case. What I mean by saying this, as I mentioned earlier, the overall goal of the data collection is to calculate the fish abundance. But here, for example, let's focus on this fish school. You see we have a fish school and its shape is like not in a box shape, but it is annotated with a school box. It doesn't affect significantly the fish abundance estimation when we integrate the corresponding pixels, because the surrounding pixels mostly contain very low intensity values. But for a pixel-wise segmentation problem, for example, it's a challenge, because then we are somehow saying this, okay, even though it is not a fish pixel, we are saying, okay, it's fish pixel. So this is why it is another challenge for this kind of problem. Also, for the supervised learning frameworks, a predefined goal in our models is also forcing to learn only the relevant features from the data, which is, for example, for sandeel, when we train our model, it is trained to learn only sandeel. So what we are interested in wider, like more broader feature representations in our case. And our research question here is how to investigate acoustic patterns with an annotation-free approach. Also, how to represent the acoustic data in a lower dimensional format, but more informative for other machine learning tasks without defining a goal in the beginning or just using the annotations. And our proposed solution to address this research question is our self-supervised learning framework here. This framework consists of two identical neural networks here, teacher and student. And this idea is based on the DINO model, which was first proposed by Facebook AI Research in 2021. And in this model architecture, we have two identical networks, teacher and student. They have the same architecture, but different parameters. And each of the networks, they contain one backbone model here, which is also called as feature extractor, because eventually we produce the feature set from the input data, followed by a projection head, a multi-layer perceptron head, to create the k-dimensional output vector, which is then forwarded to centering and temperature softmax operations to produce the resulting probability distributions PT and PS. Our main goal here is for the learning is to train the student network to mimic the teacher network's output. So the student network is trained to produce the same result with the teacher network, even though it is accepting different kinds of input data. And when we calculate those probability distributions, we calculate the gross entropy loss function. And then, based on this gross entropy loss function, we update the student parameters with Adam optimizer with weight decay, while we are updating the teacher parameters by using the exponential moving average, which is also called as momentum encoder. During the learning phase, the input data structure is also different. This is the data feeding process, for example. From the training survey data here, we extract the patches. So the sampler data selection here, the data selection procedure, which we also investigated different kinds of data selection procedures and compared. I will discuss later this one. And when we create our training patches, which is like typical, like basically the training data, which consists of 8x8 patches. By the way, we opt for 8x8 patches to capture the fine details, the high resolution. And when we have our patches, for each patch X, we extract multiple crops, local and global crops. And this illustration is for one pair of crops, like one local and one global. But for each patch, we extract several crops. And the difference here is that the teacher network accepts only local, global crops here. And the student one can take any kind, it can take local or global. The idea here is to provide more information to teacher while providing less information to student and then forcing it to learn by itself. And when we extract our crops, we also, we then resize them into the original size, 8x8. And then they are further augmented by a random horizontal flip. So this is the overall structure of our proposed self-supervised learning framework. And the idea here is to train the network by using a predefined sampling, and then use the teacher network's feature extractor to represent the acoustic data into the different formats, in a lower dimension format, but we assume that it's going to be more informative and it will increase the discriminative power of the machine learning models. So the sampling methodologies, in our case, we tested 3 different sampling methodologies here. First, for the training survey data, what we did, we extracted for all non-overlapping patches to understand the distribution of the data, actually. And then we assume that the variation within a patch is correlated to the mean values of the patches, like energy mean of the patches. And then we calculated each of them and we show the distribution of the training data. We just wanted to see what kind of distribution we have. And our first sampling method is to just completely randomly selecting patches above the seabed. And our training size is 320,000 here. So we extracted 320,000 patches above seabed completely randomly. And the resulting distribution of the mean values are something like this. Secondly, we also wanted to see if we provide a class balance data by considering the classes, as I mentioned earlier, like background, other, and sandeel. If we provide class balance data, I mean equal numbers from each class, what would be the consequence? Since we are using annotations here, it is only for benchmarking purposes. Just we wanted to see what would be the consequence. So we extracted equal numbers of patches corresponding to each class, for this case, 320,000 patches. And finally, we proposed an intensity-based sampling. We thought that, okay, if we try to just provide somehow like a more balanced data in terms of intensity, or like more stable, because the original distribution, you see, we have a scarcity here. Also, we have too many low intensity values. So we wanted to just to balance it as much as we can. What we did in this scenario, until the 95% quantile, which is minus 55 here, we divided this interval into 4 bins, like 1, 2, and 3, 4 bins. And by considering the scarcity after this part here, we took this part as a one separate single bin. And from each bin, we extracted the patches with equal probabilities. And this is our resulting distribution of the training data. And this is the summary of the sampling scheme. We call them sampling 1, sampling 2, and sampling 3 in the same order for random selection, annotation-based selection, and intensity-based selection. And what we did afterwards, because we created 3 different training data sets, and we trained our self-supervised learning framework by using those training data sets. And we we trained them for 100 epochs, by the way. And then we call their corresponding trained feature extractor as also with the same number, F1, F2, F3 for convenience, so that it would be also easier for us to follow up. Then afterwards, this is the training part. So we have trained models, trained feature extractors, and now for the evaluation, we use the separate data set because we didn't want to use the training data for this purpose. And we use a separate evaluation survey data. We again extracted 8x8 non-overlapping patches. And for each patch, we also wanted to label them. For example, if a patch is completely below the seabed, we call them as ignore class. If it contains only background, we call them as background. Sandeel, if it contains sandeel, other is the same. And in some years, some different kinds of fish species were introduced, but they are not general. They are not used for all areas. We simply ignore them. As you can see, there are quite few. And finally, if sandeel and other exist together, and it is also ignorable. What we did afterwards, we applied random undersampling, considering the least amount of the class, which is 13,800 here. We applied undersampling for background and sandeel, and eventually we had this evaluation patches here. So this is only for evaluation purposes, and we wanted to use a class balance data so that we can see the differences. And here is the overall procedure for the evaluation. I already discussed about creating the evaluation patches. And after this point, what we did. So we have 8x8 patches here, approximately like 40,000 patches here. And for each patch, here, what we did, because we have three different trained feature extractors. And for each patch, for example, we feed them to the first one, which was trained on random sampling output. And then we represented this acoustic data patch X as Z1. We call them Z1 because it is corresponding to the sampling one. We did the same for Z2 and Z3. So we had 3 different representations of the acoustic data. And finally, to compare with the untreated data version, what we did, since we have 8x8x4, we have instead of representing the data into this tensor format, we simply just vectorize them to be able to use them for the machine learning purposes. And we have V. And what we are interested here is to see the machine learning models performances when we use those different kinds of representations. And what are those machine learning models? In our case, we wanted to see the performance first for the patch classification, and we applied k-nearest neighbor model. So, and as I mentioned earlier, we have 3 different classes: sandeel, other, and background. So our KNN is simply just trying to classify our patches into 3 different formats. By the way, we split our evaluation data into training and testing. And we basically trained our model in the training set for each kind of representation, by the way. And then we tested on the same data, but with different representations. And for the patch classification, we also applied logistic regression model, again for patch classification, to be able to use detailed prediction probabilities, because we were also interested in using different threshold values and what would be the performance to have more comprehensive understanding of the model performance. And the linear regression model we used to calculate the mean SV values of the patches. By the way, here SV is the pixel values. We call them just energy intensity sometimes. But the what you see on the echogram I presented to you, they are SV values for each pixel. And our motivation to use linear regression model here is to see how well we can recover the information, because we are converting the data into a different format, different representation, and we assume that it's going to be more informative for the machine learning purposes. But are we able to recover some information afterwards? Actually, this is an important task because it relates to the eco integration for the fish abundance estimation. So we were interested in this model as well. Finally, we also used linear regression model to calculate the number of sandeel pixels within a patch to approximate the fish presence within a patch. And we wanted to see if we are able to see a good performance to capture the fish presence. And this is the result summary at the right-hand side. As you can see, we have machine learning models, as I mentioned, at the left-hand side. And for each model, we have different metrics. And for each machine learning model, when we use the data representations, when I show you here, you see Z1, Z2, Z3, and V. When we use them for those machine learning models, what the performance is, how they perform, because the only difference is the data representation for those models. And we present the best results for each row, for each machine learning model with bold font. And as you can see, if we take a line like this, all the machine learning models using generated feature set from the self-supervised learning framework are outperforming the ones using V, which is the untreated data version, the vectorized version. For example, for the KNN, the difference, the best one is the Z2, which used the annotation-based selection, while V is around 71. But for the logistic regression, it is performing, those models are significantly outperforming the one with V. By the way, they are mostly performing very close to each other, I mean the Zs, but they are always outperforming the one with V. And among those three representations, it looks like the Z3 is slightly outperforming the other ones. But at the same time, it looks like Z1, which is based on the random selection, it is performing the worst, but it is still like acceptable. It looks like this. And more details about the results. For example, for the KNN, we present here the confusion matrices. And for example, actually one like important thing arises here. When we look at the predictions of the correctly classified other classes, you see we have 1,700, 1,700, 1,700 for the Z1s here. We have Z1s and this one is V. So it is pretty low. We thought about it and we claimed that, okay, for the other class, the variation is pretty large. And for our case, we are using a very narrow data set for the other class. And probably it is not sufficient to capture the variation for the other class because we have several different kinds of fish species in the other class. But the performance for the sandeel, as you can see, the correctly classified numbers of the sandeel, it's acceptable here. It's good, actually. And compared to the one with V, it is performing better for other and sandeel class. But the KNN model based on the V, it is performing better for the background class because it has the highest number of the correctly classified background patches compared to other Z-based k-nearest neighbor methods. But we also realize that it is also over-predicting the background class because for some other ones are also predicted as background, sandeel is also predicted as background, while those numbers are lower for other methods. But the overall performance is also like Z2 is performing better, Z3 is performing very close to this one. And to compare the result with the state-of-the-art method, which is UNet model applied on the same data set, we use the trained UNet model, and then we extracted the predictions for the corresponding patches for the pixel values. And from pixel values, we also labeled the patches to produce the confusion matrix. And the UNet predictions accuracy was 71%, which is like pretty good. But we realized that the main power of the UNet model is coming from the correctly classified other classes. Here, as you can see, it's 2,200, while it is just 1,700 for the Z-generated features. And we thought that, okay, there is something to improve for the self-supervised generated features than if we should feed more data to capture the variation with the other class. But one thing interesting here is that the Z-based KNN is performing better for correctly classifying sandeel class. This also shows another promising potential for the self-supervised learning generated features here. And the results, logistic regression model, as you can again see the results summary here. Again, like the Z-based logistic regression models are performing better compared to the ones with V, and we visualize the ROC curves here, and we again realize that the worst performance is all again coming from the other class, which is shown with the orange color, as you can see, compared to the other classes, because we also have, these are class-based ROC curves. The other ones is performing, not performing good here. And the linear regression on the mean SV values to predict the mean SV values within a patch. These are the results. We visualize the predicted versus actual plot here for the linear regression model using Z1, Z2, and Z3 in the same order. We also visualize the error distributions in the box plot. And what we realize here, I mean, it's already clear that Z3 is performing better, but we saw that also the error distribution around the mean also tighter compared to other models. And we concluded, okay, for this one, Z3, the feature Z3 is more useful for this task. And the linear regression model to predict the number of sandeel pixels, we again represent the same results, in the same shape, like predicted actual versus actual, sorry, and the error distributions in a box plot shape. And we have the linear regression results for Z1, Z2, Z3, and for the V, untreated data version. And among all of them, the best one again is Z3, but we see that even though, again, the tighter distribution around the mean is coming from the Z3, but as you can see, we can say that none of the model is performing very well for this task. And the main reason of the situation is that, yeah, as you remember, we provided class balance data in terms of class balance, like background, sandeel, and other for our machine learning purpose, and we use the same data set. But here we are interested, because it's a regression problem, and we are interested in number of sandeel pixels. But almost 2/3 of the patches contain no sandeel pixels at all, because they are background or sandeel. And the number of sandeel pixels within sandeel patches, they are not uniformly distributed. You can see we have several numbers for the 64, which means that, okay, our patches completely consist of sandeel pixels. Also the other values. This is the main reason, because we didn't provide balanced data in terms of number of sandeel pixels. This is one thing that I would like to mention. But again, considering the comparison between all those models using different representations, again, Z3 is the best. And apart from the machine learning models, we also wanted to see the clustering behaviors of those feature representations. And for this purpose, what we did here, first, we are visualizing here the acoustic data. This is a portion of acoustic data here. And we are visualizing for on 200 kilohertz for simplicity. This is one portion, and the corresponding annotations here. Here, red color represents sandeel, while black is for background. So we have two classes on this echogram. background and sandeel. And what we did, from this acoustic data, we extracted non-overlapping 8x8 patches like this here. And then we forwarded those acoustic patches into our trained feature extractor, which when we used an intensity-based, the Z3 one. And then we produced the corresponding feature set. And then we applied k-means clustering with 7 clusters. Finally, we visualized their corresponding clusters here on this D. So these are the k-means cluster self-supervised features, clustering based on self-supervised features. For the same data set, we also used vectorized version of the acoustic data, and then we applied the same clustering, and then we visualize here on the C. And what we see here, when we compare, for example, let's focus on this physical. Let's focus on this physical. This is the physical in the data, and this is the corresponding annotations. And as you can see, when we take a look at the self-supervised features, it is capturing, even though the resolution is not that high, like because we are visualizing 8x8 patches here, it's capturing pretty well. And the interesting thing here is that we never use labels. Like we never say that, okay, this is sandeel, you have to learn something like this. Also, for example, for this one, for this physical, sorry, yeah. Also, on the clustering, when we used the vectorized version of the data, you see we are losing some information from the physical, for example, here, and it's not sufficiently capturing the physical at all. For example, for this one, we have a physical here, and the corresponding annotation is like this. But apparently, it is not that precise, because when we look at the physical, we see that here we have the shape something like this, but it is annotated in this way. But when we look at the features generated by our self-supervised learning, it is somehow trying to capture this shape. So it is also quite interesting for us. While for the original data representations, it is not catching those regions that sufficiently. This is one thing, and we think that it has a promising result and it has some promise. But at the same time, there are something to be improved. For example, here, the surface layer, those structures in the data, they are not fish. You can see we have nothing as annotated as fish. But for both original data and the features representations, they are somehow confused with the sandeel fish class. So this is something that we are planning to improve in this part, maybe by improving the resolution to reach the pixel-wise representation, because it is 8x8. This is also another disadvantage. But there is another thing interesting here, is that, for example, as you can see, close to the sea surface, we have an orange cluster here. So it is basically representing a layer close to the sea surface. So it has a different structure, which is not seen on the clustering when we use the original data. Yeah, these are some interesting topics. Also, the surface layer, for example, here we have a layer here. And we believe that this color is somehow like trying to capture those behaviors. And our future plans. So an interesting topic could be to extend the scope of the application, not only focusing on sandeel, but dealing with other kind of fish species. Could be really interesting to see. Also, maybe not other and sandeel, but like several different kinds of fish schools, and trying to distinguish those fish schools. So it could be an interesting topic. Also, training the self-supervised learning framework on all available data would definitely improve the model performance, because we show that we don't have to use labels to train our model. So we can basically use all the data available on our servers to train our self-supervised learning framework. And finally, investigating the uncertainty of the existing annotations could be also interesting, because as I mentioned earlier, it is the precision is not significant for fish abundance estimation, but for machine learning tasks, it is important. So we can propose a new methodology to refine the existing annotations, maybe. This is another interesting topic we are planning to work on. And sorry. And thanks for your attention. Thank you very much for listening.